Hello everyone, welcome to the fifth video. Today we're going to be talking about the WPI LIB library and how we can implement basically hardware. So everything that we need to find in terms of hardware is all in the WPI LIB library, unless we're like using some sort of software that isn't supported by the WPI LIB library, but most of everything that you'll need is there. One thing that probably isn't is like the NavX, but that's something that we can download as a dependency and then of course implement. So the first thing that I want you guys to take a look at here is the field connections. It's not entirely important that you recognize or at least memorize anything that's on here. I just want you guys to have an understanding of how the networking on the field works, and this will mainly come into play later when we talk about networks or the smart dashboard, network tables, um, and cameras, which will be in the visions video. But the first thing we're going to be talking about is drivetrains. I'm not really going to go over each and every class in specifics, just mainly because this happened in person, and most of you were there. I believe everybody was there actually, and so this is just going to be me going over through everything swiftly. But if you want to learn more about each and every class, you can just go to the bottom of this page. There's the WPI LIB reference, basically the documentation. Definitely recommend it. It's definitely a fun read, so have fun. Anyways, drivetrains. So differential drive. Differential drive is basically like your standard drive, the two sides. You have one left side that has like 3 wheels, and then the right side that has 3 wheels. It doesn't have to be 3, it could be 2, depends on the team. But basically the difference between differential drive and all the other drive classes that we see here is that the differential drive basically chains each motor controller. So you have a left side and then you have a right side, and we can see that here with this speed controller. You have a left, right, and then we create this differential drive. So the left side all moves together in union, and then the right side all moves together in union. And then if you want to turn, the left obviously slows down and the right speeds up, or vice versa, and that allows you to essentially turn. The next drive we have here is the Killoch drive, I believe is what it's called. And basically what that is this special drivetrain that essentially looks like a triangle. We don't really use that often, and you rarely see this in FRC. But if we ever decide to, make our drivetrain like that for some reason, that's where we would find that. The next class is the Mechanism drive. This was actually the class that we used in 2019, hence the example. But basically, this allows us to drive forward and backwards, left and right, and strafe, or do both at the same time, just because of the special wheels that we used. And so the Mechanism drive class allows us to use those wheels and do that sort of maneuvering. The next class here is the Vector 2D, which essentially just is a vector that allows you to store an X and a Y, and then just perform calculations if you need to. So if you're doing some sort of like motion mapping or some sort of auto, and you're trying to keep track of each X and Y on the field or something like that, I don't know what you would use that for. But that's an example for that. The WPI LIB provides various drive classes for popular drivetrain mechanisms used throughout the FRC community. Most of these classes require you to pass speed controllers when instantiating. For example, the tank drive would look like this. There's a left and right. Tank drive is differential drive, so that's why we see that. The most common methods that you will use in any of these classes will be its respective drive method, which may be arcade drive or drive Cartesian, depending on the method of driving. And what I mean by this is both the method of driving and also the drivetrain that you decide to use. So you can use drive Cartesian, or you can also do drive polar for a mechanism drive, and then this is for the differential drive. And there's arcade drive, and I'm not familiar with the other methods, but that's something you can also take a look at in the reference. Another common method, and I believe this is standard for all drivetrain classes. In fact, it is, because all drivetrain classes inherit from the robot drive base, and so the stop motor is just something in all the drivetrain classes, and basically it allows you to stop all the motor controllers with one command, so we don't have to go through each motor controller. So you can see, as you saw here, we have like these 2 motor controllers, and we'll learn more about these down here. But basically these are each an individual motor, and so whenever we want to stop, obviously we have to tell these motor controllers to stop. So that's a pain if we have a lot of those motors, but stop motor just allows us to do all of those motors in just one method. We always want the drivetrain command to be scheduled immediately. So setting the drivetrain command as the default command in the drivetrain subsystem is one of those cases where it would be appropriate to initialize the command in the init default command method of the subsystem. And if you have no idea what I'm talking about, go back and watch video 4 over command-based programming. So the next thing here is motor controllers. There's not really any reason to go into specifics about each and every motor, just because there's so many of them. But essentially, a motor controller is it's the hardware aspect, but it is the software aspect is called speed controllers. And these classes here are actually speed controllers. And so what speed controllers are is the controller to tell motor controllers how fast the motor should spin. And so motor controllers basically send that voltage to the motor, and so speed controllers tell the motor controller how much it should be sending, which essentially is saying how fast should the robot be moving. Speed controller generally depends on the motor controller. So Sparks obviously go with Spark motor controllers, Talons go with Talons motor controllers, etc. That all depends on electrical. So make sure that you are at least informed of which motor controller electrical would like to use. But again, if you just need a placeholder, these are very easy to change. The next thing we're going to be talking about is pneumatics, which is basically air and solenoids. The first class is the compressor class. This is basically how we get our air. We compress it, put them in tanks, and it's connected to the PCM, which is the pneumatic control module, and this is where all of our pneumatic stuff gets connected. So PWM is where the motor stuff gets plugged in and other sensors and whatnot, but all pneumatics have their own sort of special location where they can be connected, and that's in the pneumatic control module. The next class is the double solenoid. The double solenoid class is essentially two solenoids, which allow us to manipulate two solenoids easily, essentially. So if we want two solenoids to extend at the exact same time, we can do that because it has two channels, and so we just basically tell it to turn on. Now it's different than a regular solenoid, because if we want a regular solenoid to basically fire, we just say set true. So it takes in a boolean, which is true or false. But for double solenoids, they use this double solenoid dot value, which is an enumerator, which is sort of like a Java thing. And there's really not something that you guys have to know. Just understand that the double solenoid dot, and then there's on, off, and then default or something. So just understand that double solenoids don't take in booleans, they actually take in the special value. Something that's very important to note is that the compressor class is typically not needed when dealing with pneumatics. The reason for this is because whenever you plug in the compressor, electrical actually plugs it into a very special port, and I believe that's port 0 on the PCM. And first basically recognizes, or at least reserves that port for the compressor. And so in FRC, you basically have air pressure limits. You're not allowed to compress air beyond a certain value. Last year that was 120 psi, and so the compressor would stop once the total system pressure has reached 120 psi. And so we don't need to write any of the code that checks for that. That's already done automatically for us. And so that's why we don't really need the compressor class. But the only time you might need it is in order to see the current that it's drawing, or maybe the pressure switch valve value, which basically tells us the current system pressure. But this right here is dependent on whether or not you have fancy tech, or at least hardware. And if we don't have that, then we don't really need that. You also have the functionality to disable and enable the compressor, but this puts the compressor in an open loop state, which is something that we'll talk about in the PID lesson. But essentially, just understand that this is a huge no-no, just because in open loop, we're no longer taking in the air pressure into account. Once the compressor is in an open loop state, it's just on, and so it'll never turn off automatically. So that's a big no-no in FRC robotics, just due to safety and pressure regulations. And so if we're not stopping whenever the pressure is reaching a certain value, we're going to compress past the allowed pressure, like the allowed total pressure. And I mean, that might not be a big deal if you get to like 130, but like if we get to 200 psi, our tanks are going to blow and it's going to go boom boom on the field, and we're going to look like dummies. So it's important that we don't do that. Like I said, there's the double solenoid values enumerator. There's an on and off state. So yeah, and then regular single solenoids use booleans, which is true or off or false. The next thing is encoders. Encoders basically tell us how far a motor has turned or rotated. And so when dealing with encoders, just an important thing to note, and that's essentially what resolution the encoder is. So CPR is counts per revolution, PPR is pulses per revolution, and then LPR is lines per revolution. We want to stray away from lines per revolution encoders. These are typically found in like optical encoders, and the reason for that is because they're not reliable and they can be very inaccurate. So lines per revolution essentially is like this sort of light, and then there's some sort of indicator on your axle, and every time it turns, it checks to see if the light bounces back and it hits. And if it does that, then obviously there's been some sort of rotation made. But if that sort of indicator is missed due to like dust or something, whatever it may be, then we're not going to get reliable counts, and that can be a very bad thing if what we're trying to manipulate is very sensitive. So this year we use the default redline encoders, which have a CPR value of 1024. What this means is that the encoder essentially spins 124 times before the shaft makes a full rotation. This of course assumes that the shaft isn't geared in any way. So if your shaft is geared in any way, you actually have to perform some calculations depending on what the gear ratio is, and things of that nature, in order to basically get the amount of times the shaft is turned instead of the actual motor. So the next thing is the ultrasonic sensors. Ultrasonic sensors basically use the rangefinder class, and big thing that I want you guys to wrap your heads around is that ultrasonic sensors are incredibly inaccurate and have a lot of false readings, and so we typically want to stray away from them. They're very bad at detecting faraway objects as well as detecting close objects, so they don't really have much use in FRC, just because FRC is all about being up close and contact, but also being able to recognize objects from far away. So if we want to do any of that, we typically want to use either like driver vision or image processing or something of that nature. But ultrasonic sensors can be incredibly accurate, and it's very important that you should never make autonomous functionality completely dependent on ultrasonic sensors without proper testing first. So what this basically means is don't depend on ultrasonic sensors to do autonomous functionality just because of how inaccurate and how they get false readings all the time. What you think may be ready to do the next thing may be false just because it's getting a false reading. So the next thing here is limit switches, and limit switches, think of them as just basically buttons. We use limit switches to get the digital. We use limit switches using the digital input class, and in order to get the limit switch value, we can use digital input.get. We used the limit switch last year. We put the limit switch at the bottom of the elevator, so whenever the elevator went all the way down to the bottom, it pressed the button, and whenever it pressed that button, we knew that the elevator was at the bottom, so we could tell it to stop. But this ended up breaking the limit switch actually because gravity. So that's just one functionality of limit switches and how they can be implemented. The next thing is network tables. Network tables are basically databases on the network. The network table entry is basically a network's table entry, and then a network table instance is the instance. You generally want to use network tables when using components that connect using the radio. A great example of this is the Limelight. The Limelight has its own network table, literally called Limelight. And then its network tables entries would be like the values, so like whether or not it sees a target, or how far it is, or things of that nature. Shuffleboard also transmits data using the network tables. Network tables are basically like network databases, and you can access them looking at this code if you want to take a look at it. It's on the GitHub page, obviously. So basically, we're getting the instance of the network tables, we're getting the default instance, and then we're getting the table, which would be the name. So if you were using the Limelight would go in here. It's a string. The next thing would be network table entry, and then we would get table that get entry. This would also be a name, or string, sorry, which would be the entry name. And then the next thing is whether or not the entry is like a double or something. Then we can say get double. And then we pass in this value here as a default value in case the entry doesn't have any value. So this is just in order to protect ourselves from getting like null values or things of that nature. So the next thing here is shuffleboard and smart dashboard. We want to use shuffleboard or smart dashboard in order to provide the driver with insight on the current robot status and then some sort of feedback. So the driver would actually see the cameras on shuffleboard and smart dashboard. They also may be able to see whether or not a piston is extended or not. So we can have like a Boolean box that lights up green when it's extended or red when retracted. If you want to learn about the specific functionality within each of these, you're more than welcome to look at the library reference. There's a lot, so that's why I didn't list them. But the shuffleboard is like the modern smart dashboard. Smart dashboard is actually no longer supported. It's deprecated. And so it's no longer being supported or at least updated, but it still works. It was actually used in 2019 season. And so it's actually faster just because of how older it is. So there's not like fancy graphics and things of that nature. So it's actually a lot faster in terms of like memory. But the shuffleboard, it's a lot more intensive. And so we actually weren't able to use the shuffleboard on our computers last year just because they weren't great. And so we had to stick to the smart dashboard, which was just as great. You can do anything on the smart dashboard. Anything you can do on the smart dashboard, you can do on the shuffleboard, and anything you can do on the shuffleboard, you can do on the smart dashboard. So there's not really much of a difference except like the graphical interface. But other than that, it's all the same. So that's the WPI LIB library. If you have any questions, again, I went rather fast, but this is just an overlay of me just explaining everything. All the information is here on the GitHub page. If you have any questions, feel free to ask in the Telegram chat, and anyone can get back to you. Or if you want to ask DTRI specifically, you feel free to private message us. Cool. See you guys in the next one.